Today we're gonna have an interesting tutorial. It's gonna be about scattering and about tunneling. Wow, tunneling.
מה הייתה המילה הראשונה?
Scattering, תרגול.
כן,
And so what is tunneling? Let's think about some potential which looks like this, like a step function. Okay, meaning if this is scattering, tunneling, it comes together. So this potential, when you have a potential which looks like some V naught for x larger than 0, otherwise 0. So we can have some particle. If we are talking about classical physics, we have some objects with some energy or some velocity towards this barrier. What's going to happen? The particle will bounce back. Especially if we we can say that if the energy is larger than the barrier, the potential is equal. We know the classical particle will back, and if it's gonna bend. In quantum mechanics, it's different. Quantum mechanics, we're always gonna have a probability for the particle to go through the barrier and come back. And it's gonna be in some superposition of passing through the barrier and bouncing back.
The odds are the same? The odds are the same?
So, depends. Now we're gonna do something a little bit different, because if there is a potential at the infinite barrier, we're gonna have something a little bit different. But let's consider a simpler example where we have a finite barrier between 0 and L, and our question is, will the particle pass the barrier? So let's say we can start with the free particle. Free particle with energy h bar squared over 2m, which starts at x equals minus infinity and moves to the right. So first we notice that we shouldn't think about it as a point particle, like in classical physics. We should think about it like as some propagating wave, or some current that flows. We will see that some of this current will pass through the barrier to the other side, and some of it will get back. A probability current in quantum mechanics. So we define it as J of x, the current at some place x. So we're taking the current as some constant, h bar over m, times the imaginary part of the conjugate of psi times the derivative of psi, with respect to x. I'm not going to get to why this is true, I'm just going to take this as a given for this tutorial. Okay. Great. Questions so far? amount of probability of where the particle is.
What's the mean current of probability?
Okay. So when we talk about quantum mechanics, we don't talk about specific location, specific momentum. We talk about a PDF, probability distribution function of where the particle is, so what its momentum is. We can think about it as some kind, let's say this is the PDF. For some, let's say this is the PDF of x. We can also sometimes call it f of x or psi of x. PDF is probability density function. Funkcja wśród dystrybucji. And we can say that there is some current or some flow over time or over space, meaning that there is some movement here. We'll give you some examples.
What do you mean by movement? Like the graph is not the same.
So here there is not movement with respect to time. We talk about only with respect to x. Let's say this is this doesn't move. However,
in respect to time it will be like, I don't know, moving wave.
Yeah, but let's not talk about time, because you see the current here is with respect to space only, to the coordinate x. So basically, if I think about it, what I'm doing, I'm taking the function somehow. Let's suppose it's real. I'm taking the function and then I multiply by the derivative of this function. So I get some things that I get some function. J of x is some function that represents the current in some manners. I'm not gonna get to
The current in time.
No, the current in space. You can think about it that here it goes a little bit up, it goes a little bit down, something that relates to how much you have, which is psi of x, times how much is changing, which is the derivative.
Yeah. Okay.
Okay. So, our question is, how much will pass through the barrier and how much will get back? So we can, and I'm gonna have some general notation. I is gonna be the meaning input current or input wave. R is gonna be for return. And T is gonna be for transmitted. So return is what's coming back, transmitted is what's transmitting forward, what goes through. It's like input, in a sense. Input, I'm not sure, but inserted maybe. maybe inserted. inserted זה להכניס.
כאילו אנחנו מדברים על עובר או חוזר או מה עובר?
נכנס. נכנס, חוזר, עובר. לא, נכנס. עוד רגע יהיה דוגמה. Okay. So, when we want to look at how much is transmitted, like what's the probability of transmission or the transmission coefficient, we can say it's J transmitted. J is the current that was transmitted, over J I, the current that came in. How much transmitted is like how much came out divided by how much got inside. Similarly, the return coefficient or the reflection, we can say not return, let's use a little bit, let's use reflection. The reflection coefficient is how much was reflected divided by how much was inserted. Okay? We also can say for certain that this is, if this is the part or the percentage of how much was transmitted, and this is the percentage of how much was reflected, we can say that the sum of the two is equal to 1.
אז הרפלקשן זה החזרה. מה תגיד?
החזרה. מרגיש חופשי. אוקיי. Okay, so those are definitions. Now we want to solve it. So to solve this problem, what we're gonna do, we're gonna just use our knife and butter, which is the Schrödinger equation. We can say that H is equal to E psi of X. So when I use this equation, I assume potential is independent of time. Otherwise, I can't use this equation so freely. Okay. What is the Hamiltonian? The Hamiltonian is basically the momentum operator over 2m plus v of x. So we have here some kind of problem, because if the potential, let's say, is quadratic, harmonic oscillator, quadratic is parabola. So if it's like uniform or something which is consistent over space, okay, so if it's something, the potential is something which is consistent over space, it's very easy to just put it here. For example, v of x equals minus x squared. I could just plot it inside here and we are happy. But here we have something which acts differently over space. Okay. However, here we have something which acts differently over space. Then we must treat this equation in 3 different zones. I can call it zone 1, zone 2, and zone 3. So what we're gonna do, we're gonna split this equation, this treatment, to 3 different regimes, and then we're gonna sew up the solutions at those critical points. I call them critical points because the behavior of the potential changes abruptly. For zone 1, we have minus h1 squared over 2m dou x squared psi 1 of x equals e psi 1 of x. It's just for zone 2, we're gonna have minus h1 squared over 2m dou x squared plus v naught psi 2 of x equals e psi 2 of x. So e1, e2 minus h1 squared over 2m dou x squared psi 3 of x equals e3 psi 3 of x. Okay. So what I did here, I just split up, and I can say this is for x smaller than 0, for x between L and 0, for x larger than L. I split up space and I solved the equation, the Schrödinger equation 3 times. And this is what I got just from playing with the mathematics. Now I want to add some physics to it. Up until here we're clear, right? Mm-hmm. Great. So the physics says, okay, the total energy is something which is conserved. So I'm going to move the E1, E2, E3. Because E's energy is a constant, we give it some initial momentum or velocity, how we call it classically, which depends on the wave number k. And because we're talking about quantum physics, I'm not gonna have here particle, I'm gonna have here some wave of some sorts. Maybe I'll do it like this.
כי קשור לטענה של החלקיק, אז אני חושבת שיהיה שונה בכל אחד מהחלקים? לא. כי האנרגיה אמרנו אותו דבר בכל חלק.
אוקיי, אז השאלה?
אז מה אמרת על K עכשיו?
K is the wave, זה מספר קוונטי. האנרגיה קבועה עד שואלת האם K משתנה. So the question was, the energy is constant, so the conservation of energy. Does K remains constant? It's a great question, and I'm not going to answer it right now, because I'm going to answer it very soon. So, we can also write K is equal to K squared is equal to 2me over h bar squared. I'm going to write it for later use. So we can rearrange those equations. Blue. And I can write them as second derivative of psi equals minus 2me over h bar squared psi 1 of x. And I'm not going to write of x. We're going to assume it's psi 1 of x because we have one variable. Psi 2 second derivative is equal to minus 2m over h bar squared a minus v naught. Psi 2. Psi 3 derivative. Okay. I'm gonna write here, I write here two things. So the first one is that K squared is equal to 2me over h bar squared. And the second thing, I'm gonna define Q squared, and I'm gonna write it as 2m e minus v naught over h bar squared. Any questions so far? Yes, definitions I can write as 3 lines. I'm going to try to be consistent. So, if it's all clear, I can just delete this. And instead write, so we have here minus k squared psi 1 minus q squared psi 1 minus k squared psi 1. Very nice. This is very easy to solve, right? This is very easy to solve. You know how to solve those equations. But let's think about this q squared for a second. This q squared. Okay, let's solve it first. Let's just solve it. And then think. A lot of the times it's good to just do the analytics and then say what the hell did I do? to sine 1 of x, which is equal to e I k x plus b e minus I k x for x smaller than 0. Sine 2 of x is equal to a e I q x plus, let's call it c plus d e b minus I q x for x between n and 0. Sine 3 of x is equal to e I k x plus f e to the minus I k x. Are we happy?
Yes. No?
Are you happy? Any questions? What we did so far? So you're happy?
Kind of.
Kind of.
If I'm happy.
Do me a favor. Okay. And we're gonna also write here that the energy is equal to h bar squared k squared over 2m. And let's think about what the hell did we wrote over here. So what we have, which goes is a e to the I k x, and here to the left is b e to the minus I k x. Okay, so first of all, we look at sine 1 of x. This is a summation of wave functions, both of them with wave number k. One goes to the right and one goes to the left. So it is clear to say that e to the x it is the input, the inserted wave, what we have that came from x comes from minus infinity. This is what we have as a start. And b to the minus x is what we have that is reflected from the barrier. Perfect. What we have in the middle we have, similarly, c e to the I q x to the right, and d e to the minus I q x to the left. So, let's think about this q right now. Okay, so first of all, what we have here on the left, we know k is something which is real. It's like some integer. Or maybe not even an integer. We know it's probably an integer. Let's assume it's something which is real. So here we have an oscillation. Because e to the I, something real, gives cosine and sine. But do we have here in the middle also?
Only if the energy is smaller than...
Only if the energy is larger than V naught.
If it's larger, why it's...
If it's larger, q squared is something which is positive.
Yes.
Meaning q. Okay, let's go the other way around. If q squared is larger than 0, q must be some I to some constant. If q squared is larger than 0, so q can be real.
And if q is real, there's no current?
I didn't say it.
Huh?
I didn't say so.
You did it.
We're gonna get there.
Okay.
We're gonna start. What I'm gonna emphasize right now is that if we have more energy, if our energy is larger than the potential barrier, we're gonna have oscillations here. If it is smaller, we're gonna have exponential decay. So let's give it a red marker. If E is smaller than V naught, what we're gonna have? We're gonna have some wave. I don't know, maybe have here is e to the minus ix. Because q e minus e naught over a. And we can calculate I v naught times e over h over c. So q is imaginary, and I have I times times, let's say this is I times constant, I times C1, which is equal to C E times sometimes x. So exponential decay, and it's very important because it gives us an intuition that if the wave is too high, we're still going to have some wave which propagates through the barrier, but it's going to decay very, very rapidly, very fast. The decay is going to be very, very strong. Okay. On the right side, we are going to have to the right capital E, small e to the ikx, and to the left fe to the minus ikx. Because here we have oscillations, and here we have the same waves up until some factor e over a, but here we're also going to have oscillations, which makes sense because we assume that the energy we have is something positive, larger than 0. So it always has some energy which is larger than the potential it hovers over. Hence we have some wave which propagates. What about this? What can I say about the wave, the reflected wave in this zone? I can say it is nonsense.
כי אין נקודה שהפוטנציאל משתנה בה.
Because we cannot, yes, almost. The more precise way to say it is we have some wave comes to here, some gets reflected and some gets transmitted and goes to infinity. Nothing ever gets reflected from x larger than L. מצטער, זו סבתא שלי. סבתא משהו דחוף. אז אני אחזור אלייך. אני אחזור אלייך. זה לא משהו דחוף, אבל רגע. טוב, תחזור אלייך. Okay. Great. So, let's get to business. Our question is, how much gets transmitted or reflected? Let's get with how much gets reflected. So what we are interested is in JR and JI. What is JR? It's H bar over M, and I can write here JR over X. I'm going to do it just once. The imaginary part, and I'm going to look JR, what's the reflected part? The reflected part is this part, the part of the B. So we can can define on the right side 1 of x. But it is not what's reflected. It's only the part of b e to the I kx which gets reflected. So I can write here conjugate of b e to the I kx, because it had here minus, that's the conjugate, times dx of b e to the minus I kx. H bar over m, imaginary part of b e to the I kx times b minus I k times e to the minus I kx.
יש לי שאלה. אז זה של DE ומינוס IQ X. אמרנו משהו שדועך, אבל עדיין ילך ימינה בעצם, הוא לא יחזור.
DE ומינוס I kx הולך שמאלה. המינוס נותן פה את הכיוון.
זרם שחוזר?
DE במינוס IQX זה הזרם שחוזר מ-X שווה N.
נכון.
עכשיו, אין סיבה שהוא ידח אקספוננציאלית. אין סיבה שהוא ידח אקספוננציאלית אם Q הוא מדומה. כלומר, פוטנציאל יותר גבוה מהאנרגיה, אז הוא ידח אקספוננציאלית שמאלה, זאת אומרת יהיה לי זרם. להחליף לאנגלית, עוד זה שבאתי את זה. Question was regarding this DE to the minus IQX. So we have something over here. We have a current that decays exponentially to the right, which is the CE to the IQX. This is for E smaller than V naught. What I'm saying is we're also going to have some current which decays exponentially to the left. If E, for the case that E is larger than V naught, we're going to have some oscillations to the right and some oscillations to the left.
So when we talk about the JR, we don't need to...
JR is the reflected part. Okay, so we might have...
reflecting from X...
Let's say we have some maybe 4 layers. We want to know how much totally is reflected. Then let's say we have some input, IR, and some reflected, and we have some transmitted. So I can calculate how much is reflected and transmitted for each of the rays, but in total, what I'm going to have here is the total reflection, and here is going to be the total transmission. ומעכשיו אני אענה פשוט בעברית, כי זה רק סיני אחד, למה אני אענה בכלל בשאלות כאלה באנגלית? אוקיי.
רגע, אז יש לי שאלה.
כן.
בגלים למדנו שיש העברה והחזרה, הוא קרא לה קבועי גל לקיים בשמות שונים, והיינו צריכים לחשב אותם, זה יצא תוצאות
כאילו... כן,
אז הנקודה שמה שבאתי להגיד, איך קוראים לזה? אז ה-K של ה-BE, בתוכו גם את הרכיב של ה-Q, כביכול...
יש ביניהם, ואותו נמצא על ידי תפירת תנאי השפה.
זהו.
יש ביניהם קשר.
אז עד כה זה פשוט כאילו ממש כמו שלמדנו בגלים, רק שאנחנו לא מכריחים שזה יהיה יותר פונקציית גל. כאילו אני...
לא מכריחים, מתישהו, אם נרצה לפתור את זה כמו שצריך, עד הסוף נצטרך גם לתפור את התנאים פה ופה.
כן, אבל...
נצטרך, ואז כשנתפור את התנאי שפה, נקבל קשר ברור בין K ל-Q.
אז במה זה שונה נגיד מסתם כאילו גל שנכנס...
סתם גל שנכנס. אז
כרגע אנחנו עושים סתם גל שנכנס, נקדם העברה החזרה.
כן.
ופשוט... כאילו שזה בדיד.
איזה הנחות? איפה הנחתי את זה?
תכלס עוד לא הנחנו את זה.
לא,
נכון, לא אמרנו את זה. אוקיי.
יכול להיות שבקורס מגנים פתרת את אותה השאלה.
כן.
כן, כאילו עוד אין פה משהו קוונטי.
לא.
אין פה התנהגות קוונטית כרגע. במה שעשינו עד הרגע. אנחנו אומרים, גל עובר, אז כאילו...
ההתנהגות הקוונטית זה כשאנחנו אומרים שהגל הזה הוא בעצם איזשהו חומר. וחומר באופן קלאסי לא יכול לעבור דרך מחסום. חומר לא דועך אקספוננציאלית לתוך מחסום שגדול מכמות האנרגיה שלו. אז בעצם המתמטיקה לא השתנתה, הפיזיקה כן. אולי לא גם לא.
אז אם בגלים כאילו דיברנו על הכל, אז פה אנחנו מדברים על חומר.
גם בגלים אנחנו מדברים על אותו דבר, בסופו של דבר זה אותו דבר. אם זאת המטרה של הפיזיקה.
למדנו את הגלים ממש כאילו גל דועך בתוך חומר וכאילו מה...
אבל אנחנו עומדים
עד כה זה סיים.
לא יודע? אז אני יכול לרוץ על זה.
כן.
סתם, תתחיל, אני רק נעצור אותך.
כן. ברגע שזה יהיה קצת מוגזם.
So,
בינתיים תעבור.
the current is, as mentioned here, h bar over m imaginary file of absolute value of b times minus k, which is equal to minus k absolute value of b squared. Minus h bar k over m b squared. Okay, on the other hand, I can calculate j inserted over x, which is equal to h bar over m, the imaginary part of a star e to the minus I k x d to the x of the conjugate of this is gonna be I k a e to the I k x, which is equal to h bar k over m times b squared. Questions? Great. We don't have any. Yes.
רגע. הסוגריים המסולסלים.
It's for the imaginary. Take the imaginary part.
זה גם בהרצאה, זה לא האופרטור שעושה מכפיל כאילו, עושה מכפלה פנימית ומחליף את הסדר, ומחליף פעם ככה ופעם ככה.
אני לא יודע מה אתה אומר, אבל יכול להיות שיש אופרטור שעושה את ה-imaginary. נראה לי יש אופרטור כזה.
כאילו אנחנו מקבלים דלטה פה, זה כל הקטע, ואז בגלל זה זה פשוט
imaginary
b בריבוע IK.
של a ועוד b.
אוקיי.
שאלות? אוקיי. אני מוחק את זה, כי אולי לא הייתי צריך למחוק את זה, וזה בסדר, נורא. בכל מקרה, anyway, I deleted this file because I decided to, and anyways, so what is the reflection coefficient? The reflection coefficient is JR over JI, absolute value, which is an absolute value of minus h by k over m.
It's the reflection for part 1, okay?
This is the reflection.
Because in part 2 we have reflection as well.
Right, but we wanted to do the total reflection of the particle from the barrier. So even if we have 10 barriers, we don't care. We care only about in a sense we care only about the first one, but if we will solve it more, okay, so we're going to talk about it in 1 second. So let's do the mathematics first. It's h bar k over n a squared, and this is b over a absolute value squared. And the transmitted is 1 minus r. So we solved the problem. Not really. Why not really? Because we don't know what a and b are. To calculate a and b, we will have to sew up the solutions to connect the solutions at x equals 1, x equals r. And we're gonna have to impose some conditions to make it connect. So the wave function is continuous, and also maybe the derivative, maybe not. Over here, the derivative is not continuous. But in general, we got the idea. Questions before I erase everything. Okay. Now we're gonna do an easier example, which is gonna be very similar. Let's start. We're gonna do a step potential. מה המצב? כיף?
מה?
יונתן לא נראה לי מבסוט.
אני נהנית, מה איתך?
פשוט אבל לא, עד כה זה גלים וזה אחד הקורסים האהובים עליי, כאילו.
רואה, זה הפרצוף הנהנה שלו.
זה הפרצוף הנהנה. זה הפרצוף האהוב שלו. זה היום. צריך טישו קצת לפרצוף הנהנה?
מאוד שלו שלו.
טוב. psi of x is equal to a e to the I kx or b e to the minus I kx for x smaller than 0, and c e to the I qx for x larger than 0. This is the same in the same method we solved it previously, where I don't have a dE to the minus I qx because I don't have anything which is reflected back. Okay. In the same manner as before, I'm gonna define k squared is equal to me over h bar squared, and q squared is equal to 2m e minus b naught over h bar squared. If some of it is not clear, just take it as granted for now. Just because if it's not clear, go on the start of the lecture again. And I'm gonna write, just for completeness, I'm gonna write I is equal to j r over j I. T is equal to JT over JI. Okay. So let's solve for the probability constant. What is Ji of x? So h bar over m, imaginary part of, and I can write a conjugate e to the minus I k x times I k a e to the I k x. This is equal to h bar k minus over the minus without the minus over m times a squared. Is this trivial by now? We can keep going solving those coins. It's trivial? Okay, let's assume this is trivial. So I can write JR of x. It's going to be minus h bar k over m b squared, and JT of x is going to be h bar q over m times c squared. So here the reflected is b over a squared, and the transmitted is q over k times c over a squared. Okay, it's a little bit to take in. What we got here. So here, for the reflected, we got the same result as before. We got what's reflected. Let's have it a e to the I k x, b e to the minus I k x, c e to the I q x. How much is reflected is, in a sense, the ratio between those coefficients squared. Squared is because A and B are like some kind of probability coefficients. However, for the transmitted, we have this ratio of k over q. It's a little bit weird in some sense, and the reason we get it is to conserve energy. In some sense, because we moved from one regime, one surface to another surface. It's like when we have in optics that we move from air to water. So here we moved from one potential to another potential. We have some coefficients which pops out. We will see later that it's still that we need it to have that r plus t equals 1. Question.
אתה אומר שזה יצא קווים כי עברנו לתווך אינסופי בניגוד
לא אינסופי. למה אינסופי? תווך אחר.
כי קודם היינו במקום מוגבל ועכשיו אנחנו פשוט עולים מדרגה ו...
למה? גם פה זה אינסופי, יש מינוס אינסוף עד 0. פה זה מ-0 עד אינסוף.
נכון, אבל בחלק הזה יצא לנו אותו דבר.
אבל...
לא, היה פה מעבר לשני טווחים, אין פה כזה שאלה.
לא אכפת מה קורה בצד השני, ביציאה.
גם אם זה היה סופי,
גם
בדיוק, גם בתקופה הקודמת הייתי מקבל את אותו דבר. גם בתקופה הקודמת הייתי מקבל את אותו דבר, כי הדבר הזה לא קשור לסופיות או אינסופיות. זה רק אומר, רק עשיתי פה סוג של יחס בין הדברים, וראיתי שפה בטרנסמיטד יש לי Q, באינפוט יש לי K, וזה קפץ. ועכשיו למה זה קפץ? ההסבר האינטואיטיבי למה זה קפץ, זה שיש לי פה שני טווחים שונים. יכול לחשוב זה כמו שאור שעובר ממים לאוויר, או מאוויר למים. אז אנחנו בגלים ובאופטיקה אנחנו רואים שיוצא איזה קבוע מחוץ למקדמי ההחזרה להעברה. אז הקבוע הזה זה מאותן סיבות של קשורות לשימור אנרגיה, שהגל, אתה יכול לחשוב על זה שהגל הרי, פה יש לי here I have e to the I k x, כאן יש לי e to the I k x, זאת אומרת יש לי איזשהו גל, מספר גל מסוים, פה מספר הגל משתנה. אם מספר הגל משתנה, אז בשביל שימור אנרגיה אני צריך עוד איזה מקדם שיאזן את זה. והוא בא באופן אוטומטי, זה לא שאני מכניס אותו בכוח.
השאלה אם באמת כשיש לנו כן החזרה משני הצדדים, כאילו, כי נגיד קודם...
מה זה החזרה משני הצדדים?
אוקיי, אז...
נגיד מחסום פוטנציאל סופי.
לא, כי השאלה היא כי... אני אנסח את עצמי יותר טוב. בשאלה, בפעם הקודמת אמרנו ש... בית יפה.
אני רוצה לבלבל את הסצנה.
כן.
כן, אני מקשיב.
אוקיי, טוב. ש-D חוזר, כשעשינו את אותו דבר עם D, ותיארנו גם גל שחוזר בתוך התווך כביכול.
נכון, אז זה נגיד...
אז הוא מוכלל, אז בגלל שאנחנו מדברים על הטוטל קרנט, אז אנחנו לא, ופה לא דיברנו על D, אז האם כאילו אנחנו נקבל...
נקבל את אותו דבר.
אותו דבר, אנחנו לא נקבל איזה קבוע שונה, או ש...
כי גם היה פה ועוד, אם היה פה פלוס D, D מינוס IQX, עדיין בטרנסמיטד, אנחנו נגיד טוב, טרנסמיטד זה רק החלק של ה-C, כמו שפה ברפלקטד הסתכלנו רק על B, רק B הוא רפלקטד, והאינסרטד זה רק ה-A.
הבנתי, אז מראש אתה מתאר את המערכת בצורה הזו, ככה ש-B כולל את כל מה שיוצא.
נכון, זה חייב. ככה או ככה B כולל את כל מה שיוצא, לא משנה מה קורה פה בהמשך, B כולל את כל מה שיוצא. איך זה יבוא לידי ביטוי, מה קרה בהמשך? מתי זה יבוא לידי ביטוי? זה יבוא לידי ביטוי כשנבצע תפירה של תנאי שפה.
אז פה נגיד איך היית מבצע תפירה של תנאי שפה,
שאלה נהדרת.
D לא היה צריך כאילו...
D של 0, בטח ש-D היה צריך להיכנס.
אז למה פה לא כתבנו את D?
כי פה אין לך גל חוזר. זו דוגמה קצת יותר פשוטה.
פה אתה מניח או ש... אז מה אתה...
את הדוגמה עם D, אתה יכול לעשות למשל בשיעורי בית. זה נהדר.
אוקיי.
זה היה נהדר, אני לא אוהב לך את זה.
אוקיי,
אבל פה זו דוגמה קצת יותר פשוטה, לצורך התרגול.
הבנתי.
אבל הפעולה, מה שאתה צריך לעשות, התפילה של תנאי שפה היא באותה צורה. So this was regarding the sheep. אוקיי. זה היה כזה מצחיק. Okay, so now we want to do the boundary conditions. We want to connect the wave function on the left side and on the right side. Okay, so how we do it? We say that we use the continuity conditions. So we said that P of the psi of 0 minus is equal to psi of 0 plus, for example. So the wave function must be continuous no matter what. Regarding the derivative, it says it must be is that the derivative must also be continuous. So the derivative at 0 minus must be the derivative of psi at 0 plus. So from here we can just put 0 in x on both sides and we get that a plus b is equal to c. From here that ik a minus d is equal to iq times c. Okay. So I'm gonna do some trick here because what we have here, we have two equations with three variables. So where is the third equation can come from? The third equation can come from normalization. However, we don't need to, because all we care about is not about A, B, and C individually. We care only about the ratio between B and A, and C and A. So I can write it as 1 plus B over A is equal to C over A, and this I can write as IK1 minus B over A is equal to, let's remove the I, to Q times C over A. And let's write it. So using this first equation, which I'm gonna leave it here for the time being, and this equation, we have two equations with two variables. The variables being C over A and B over A. So I don't want to go over the steps and solve it exactly, because I think it's a waste of time. So I can just write to you that after some algebra, B over A is equal to K minus Q over K plus Q, and C over A is equal to 2K over K plus Q. Does anyone want me to do the algebra? Great. So for the reflected part, we have K minus Q over K plus Q, absolute value squared. We can just say, and now we can take the definition of K and Q after we take the square root, do some calculations, and get to 2 minus V naught over E minus 2 square root. Okay, let's write it bigger and nicer. So from here, the reflected part and the transmitted part are trivial in a sense that it's only some hard algebra. I'm going to write the solution because I want to discuss it. Okay. So the solution is R is equal to 2 minus V naught over E minus 2 square root of 1 minus V naught over E divided by 2 minus V naught over E minus plus 2 square root of 1 minus V naught over E. The transmitted part is 4 times square root of 1 minus V naught over E over E plus 2 square root of 1 minus V naught over E. Okay. And of course we can check it and get that T plus I is equal to 1. It is very easy to see. How is it very easy to see? Because, how is it very easy to see? This looks very easy to me. Because okay, it's very easy to see because what we have when we add this up, so the denominator is the same, but the numerator, here we have minus 2, here we have plus 4, so we get in total plus 2. So we get 1 because we get the same expression. But what is interesting is what happens, because they are physicists, and physicists don't stop with the final solution. Physicists stop when they understand the system. So what happens when E is very, very large? Meaning larger, very, very large with respect to the potential. So before we consider the analytical solution, what is supposed to happen when the energy is large, very, very large? We have infinite amount of energy. So if a particle has so much energy, you wouldn't even see the barrier, which has some negligible influence. So we expect that for this case, we expect R to be 0 and T to be 1. So for this case, we expect that R will be 0 and T will be 1. For very small energy, with respect to the potential, we expect that everything will be returned and nothing will be transmitted. In this case, we can write that V naught over E is very small, and here we can write that V naught over E is very large, right? Right. You agree about the blue stuff? I just divided here by E and here by E. So let's see if these limit conditions work. So when VE is very, very large, this blue object, which appears here, 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 and here, and here, and here, and here, is negligible. So what we have for the reflected is 2 minus 2, 0. You can check if we have 2 over 4. Here we have 4 times 1 divided by 2 plus 2. For when this blue object is huge, we can say that we have here the blue object times 2 square root of the blue object. V naught over E larger than 1. Here we have the blue minus minus 2 square root of smiley plus 2 over square root of smiley. It makes sense. And then here we have minus and minus, which doesn't matter, it cancels out. For the transmitted part, this is R, the transmitted part, what we have is 4 times square root of this smiley divided by by smiley, so it goes to 0. Basically, because square root of smiley over smiley is 0 when smiley goes to infinity. And we're happy. Questions? Jonathan, are you happier now?
I'm always
Nah.
Okay. I have a few questions.
Sure.
רגע. עוד כמה זמן יש לתרגול?
יש עוד דוגמה אחת.
אז אחרי, כי זה לא קשור.
לא קשור. אוקיי. never mind, never mind.
אתה יודע שיש לך שם אחת, אולי זה יהיה לך...
לא זה. Okay, last example. Let's do it quick. So, the last example is going to be some delta potential. V of x to beta of x. case, what we're gonna have, we're gonna solve the equation x explicitly. We're gonna have minus h1 squared over 2m x squared psi of x plus delta of x psi of x equal e psi of x. Okay, great. So for x not equal 0, meaning x larger than 0 or x smaller than 0, we get that minus h bar square over 2m dou x squared psi of x is equal e psi of x. Because this potential is a point potential, it's a delta function. So only when x is equal exactly 0, we're gonna feel the potential. So it's a little bit weird because what we say is basically at all space but a specific point, everything is regular. But this point is very strong. How strong? Infinitely strong, because delta x it goes to some infinity in a sense that an integration over it gives you only 1. So it's some finite infinity maybe. It's infinity in the sense that when we have a delta function, this we take the width or the variance or the standard deviation or variance, doesn't matter, we take it to 0 such that the height, let's put h, goes to infinity. This we do it in a manner that the height minus the variance go to something finite. A good example, I think it's important to talk about, is that we can define delta of x as a Gaussian at the limit of the variance which goes to 0, e to the minus x squared over 2 sigma squared divided by square root of 2 pi sigma squared. We can. This is one definition. It's an equality. It's not an approximation. It's an equality. We just take a Gaussian and we use it because it's normal. Meaning the integration over all space would be always 1, no matter what the parameters are. Parameters being only sigma. However, we take sigma to 0. And so we get a delta function. Questions about delta functions?
כשכתבת את השרדינגר למטה, את הדלטה?
כן.
למה?
באזור בו x לא שווה ל-0.
מה זה? מה שם x גדול מ-0 ואז b?
או, זה או. או.
אוקיי.
או. לא יודע. מבלבל קצת. אוקיי, let's continue. So, psi of x, we can express psi of x as e to the I kx plus b e to the minus I kx for x smaller than 0, but for x larger than 0, we have only ce to the I kx, right? Kx. Here, I didn't change the k, because the potential on the left side and on the right side is the same. Because k is equal q, I can say, okay, we don't care about q anymore. Let's do this there. We don't care about q anymore, and k is equal q, so I can remove this. So the reflection and the transmission ratios stay the same, and I don't need to change the constants because I was consistent with what we did in this class. So this is still valid, everything which is written over here. Questions? Great. So boundary conditions. Let's find out the coefficients. again, we don't care about. Okay, so let's use the continuity of psi. So for the continuity of psi around 0, we can say that a plus b is equal c, meaning, let's use the razor, meaning 1 plus a, 1 plus b over a equal to c over a. Right. Now, let's look at the derivative. The derivative is not continuous anymore, because we have a delta function. What can we do? Yamsuf, what can we do?
When the derivative is non-differentiable,
We can integrate.
okay.
Okay, what does it mean? We can say that we can consider this equation and just take an integral over x between this point, which you can call it 0 minus, to this point, which you can call it 0 minus. I'm going to write it down at the next step. So minus h bar squared over 2m integral from 0 minus to 0 plus dou x squared of dx plus beta integral from 0 minus to 0 plus delta x psi of x is equal to e times an integral from 0 minus to 0 plus psi of x dx. Very interesting what I did. Or if I would do the same thing, I would simply write, let's say I don't have the delta part. Let's ignore it first. Let's say this is ignore. Ignore. What we're gonna get is, we're gonna get here minus h bar squared over 2 psi tag, derivative of psi, and I can derivative of psi of 0 minus psi tag, derivative of psi at 0 plus, or plus here and minus here, and then plus ignore is equal to, here this is the density function. So what is the probability to be in some infinitely small space? 0. Okay? Right? So what we got here is the continuity of the derivative. In Hebrew, מה שקיבלנו פה זה בעצם זה שקודם היה לנו שנת הרציפות. רציפות הפונקציה, רציפות הנגזרת. פה קיבלנו את רציפות הנגזרת. So what we did here is we show another way. We can always, if the Schrödinger equation is correct, always, I can always take the derivative of both sides. I can also always integrate over both sides. And the integration could be over anywhere I want, because this is correct for any x. So I can specifically choose to integrate from 0 minus to 0 plus. Do you feel convenient with these integration boundaries?
Okay.
Okay? So if we ignore this part for a second, we get what we get usually. Meaning, if we don't have some delta function, there's a condition that the derivative of psi must be continuous. However, we can't ignore it. We can't ignore it because it's almost infinite at some point. And by definition of the delta function, what we get here is beta psi of 0. Okay. Gonna get another step ahead. So minus h bar squared, and that's over 2m times okay. Sine okay. So minus h bar squared over 2m. Psi of 0 naught is so ik c to the ik times 0 minus a, and here I have c e to the 0. I can just, I'm not gonna write exponential. Just do this. So ikc minus, and here I'm gonna have ika minus ikb is equal to minus beta, and I can write whatever. Psi of 0 it's the same because we know that a plus b is equal to c. So for example, I can write let's say beta times c, and that's it. Okay. So algebra ahead, which I don't want to do algebra. Let's give it another step. So ikc minus ika plus ikb is equal to 2m beta over h bar squared c. Okay, we can divide anything by a, everything by a, so we have here c over a, here I have 1, here I have b over a, and here I have c over a. We are done. When we are done, we have two equations with two variables. With two unknown variables, b over a and c over a. So for me it's trivial to solve questions of what we did. I'm gonna erase.
יש עוד דברים שאנחנו צריכים לעבור עליהם?
No, basically that's it. We're gonna have one more slight point. Okay. What? Okay. So the transmitted coefficient is h bar to the 4th k to the cube the k squared h bar to the 4th k squared plus m squared beta squared. And the reflected is m squared beta squared over h bar to the 4 k squared plus m squared beta squared. So when beta goes to 0, we have that transmitted is 1, reflected is 0. When beta goes to infinity, we have that transmitted is 0, reflected is 1. Meaning, when the width of the delta potential is infinitely strong, nothing gets passed, nothing gets transmitted, everything gets reflected. When the width is infinitely thin or small, everything gets passed. We don't see the barrier at all, and nothing gets reflected. Okay, that's all. Okay. שאלות?
Yes.
יאללה.
יש. שמעתי לי. אוקיי, סבבה. שאלה אחת על נוסף להתחלה, על הדלתה. אז אמרת שאתה... לא, בסדר לי. שלנו שתיארת את הדאטה גאוסיאן חייב להיות כאילו 0. יש לזה משמעות מסוימת.
מה אני אמרתי?
הסיבה...
ממוצע אתה מתכוון?
כן.
לא, אני אמרתי
הווריאנט.
סיגמה, וריאנט, שהוא צריך להיות לא את
לא.
האפס.
סבבה, אבל כשרשמת את זה, רשמת את זה עם E במקום X מינוס מיו בגבורה.
לא, זה לא חייב.
זה לא חייב להיות 0, זה גם שהווריאנס יהיה 0.
כן, אבל כי אמרתי דאטה של X. אם הייתי אומר דאטה של X פחות X0, אז במקום X הייתי עושה X0, ו-X0 זה היה ממוצע.
כן, אוקיי, זהו, זה מה שרציתי לוודא. אוקיי.
אתה רוצה לסיים?
כן.
שאני אשלח לך במייל פשוט?
אני רוצה לך מייל שלי.
מה אתה רוצה, את התרגול?
כנראה, אבל שגיל.
אתה רוצה את התרגול פשוט?
לא, בסדר. זה במודל?
אני יודע את זה המודל, אבל זה גם בדרייב.
אוקיי, סבבה. בכל זאת.
כן, יש לי כתב קשוח.
בסדר, שיהיה, זה רק הסוף שם שרציתי שיהיה לי מסודר. אז תביא, אני אכתוב כי זה לוקח, זה מייל מסובך. אוקיי, עוד שאלה. לפי מה אנחנו אומרים ואיך אנחנו אומרים שמתכנס, כאילו הבטא